Day, class. Yes, today is Tuesday. It is the second day of your spring break. That means you've either watched this today or you have watched it on Friday or Saturday or Sunday, hoping to get them all done before the end of the week. Entirely your choice. Nobody's going to force you to do anything that you don't want to do because that's the way life goes until you actually get a boss, and then your boss is going to make you do whatever needs to be done. So get used to it now. So like I said, this is the second day. Hopefully the first lesson wasn't too difficult for you. Hopefully you got through the scale factors. Hopefully you got through what you needed to get through. Today's lesson, we're actually going to be using scale drawings, and we're actually going to do some solving area problems. Now, it's very important that you remember your areas, like pi r squared for a circle. It is important that you know length times width for a rectangle. S squared for a square. It's imperative that you know these because you can't guarantee that you're going to have a cheat sheet on your 10-ready test. They might give you one, they might not. So you need to make sure you can compute these back from memory when it comes time to use them. All right, so let's get down to it. So lesson 15, this is, we started in lesson 13, so if you're paying attention, we're skipping lesson 14 and we're going to 15. So that means we're actually doing one less lesson than we should be doing, and that's fine because lesson 14 was kind of a lot of review information anyways and isn't really necessary to what we're trying to accomplish. So lesson 15, solving area problems using scale drawings. Now, Mr. Haley, you're asking yourselves, scale drawings? So are we going to be using scale factors still? Absolutely, that's the key. We're using scale factors. We're going to take what we learned yesterday and we're going to apply it to what we're doing today. So, yes, if you notice, I'm going to say so a lot. If you want to calculate how many times I say so in the video, that is perfectly acceptable for me. So, opening exercise. For each diagram, drawing 2 is a scale drawing of drawing 1. So drawing 2 is the scale drawing of drawing 1. So that means drawing 1's the original, drawing 2 is the scale. So complete the accompanying charts. For each drawing, identify the side lengths, determine the area, and compute the scale factor. Convert each scale factor into a fraction and percent, examine the results, and write a conclusion relating scale factors to area. So obviously you can tell that we're going to be working with scale factors, and we're looking at area. So that means somehow, some way, the two have to be related. If this whole lesson is about solving area problems using scale, then scale factor has got to come into play somehow. Now, if you remember when we did our scale factors in Monday's lesson, scale factor is when you take the scale drawing and you divide it by the original. So which one's the scale again? Drawing 2. Which one's the scale? Drawing 2. Which one's the original? Drawing 1. Which one's the original? Yo, drawing 1's the original, dude. Yeah. Let's see. I'm going to hear this from y'all in the morning when we get back from school. All right, so drawing 1, what's the other side length? Well, drawing 1 has a side length of what? Yeah, it just has 3 units. So what's the side length of drawing 2? 9 units. I'm so proud of you. Y'all are making me so happy. Yes, include you, Coriana and Takata. Y'all made me so proud. See, I got a big giant smile on my face. So happy. All right, scale factor is a fraction and percent. Now, we told you the scale factor is when you take the scale over the original. What's the scale factor drawing again? That's right, drawing 2 is the scale. So 9 is our scale unit, and 3 is our original. So what's 9 divided by 3? It's just going to be 3. So what's 3 as a percent? It's 300%. Okay, so our scale factor as a fraction is 9/3, and our percent is 300%. So drawing 2 is 300% larger than drawing 1. Now, let's do some calculation of the area. Okay, so let's go ahead and see, I'm looking ahead, I'm seeing scale factor. So let me go ahead and write the scale factor. Scale factor was 3. All right, so the quotient of the area. So let's find out what the area is. So the area of a square is just the length times the width. So the area of drawing 1's 3 times 3, which would be 9 units squared. And then drawing 2 would be 9 times 9, or 81 units squared. So what's the scale factor of this one? Well, we're going to do the same thing. It's got to be drawing 2 over drawing 1. So this time the area is 81 over 9, which reduces to 9. And that as a percent would be 900%. So the quotient of the areas was going to be 9. That's kind of interesting. Now, my hypothesis at the very beginning would have been that the quotient of the areas and the scale factor should have been identical. But in this case here, to find the quotient of the areas, you take the scale factor and you square it. And you're asking, Mr. Hale, what are you talking about? Well, think about it. The scale factor is 3. If I take 3 squared means 3 times 3. Does 3 times 3 not equal 9? It does. So my conclusion is that to identify the area of two figures that are scale drawings of each other, all I have to do is find the scale factor of those drawings and then square that number to find the area, to find the scale factor that represents the area of those shapes. That's interesting. So that's very intriguing. Let's see if that conclusion actually applies to the next problems. So let's go look at the next one. Okay. Oh, we got circles. Circles, circles, circles. What do we do with circles? How do we find the circle? How do we find the area of a circle? Is it 2 pi r? Is it pi times d? Or is it pi r squared? Oh, I'm disappointed in you, Jalen. It is not 2 pi r. I am disappointed. It is pi r squared. Define the area of any shape. Area equals pi r squared when it comes to circles. Okay, now let's go back and let's take a look at the previous slide again, because it's important that we recognize something. For each diagram, drawing 2 is the scale drawing of 1. So drawing 2 is always going to be our scale. So this is our scale. This is our original. So we need to identify the radius of both drawing 1 and drawing 2. How do you know that, Mr. Hill? Well, take a look at the column, radius. I need to find the radius. Well, how do I find the radius? That's right. I start at the center and count outwards. So here's the center. So that's 1, 2, 3, 4. So my radius of drawing 1 is 4 units. Okay, so drawing 2. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 units. Okay, so what's my scale factor? Right, I'm going to take since drawing 2 is obviously bigger than drawing 1, it's an enlargement. So that means my scale factor is going to be 8 over 4, which equals 2, which would be 200%. How did you find out it was 200%, Mr. Hale? Remember, all you got to do is take the scale factor and multiply it by 100 to find your percent. That's it. That's all we're doing. All right, now, if we base our conclusion off of what we learned yesterday, or not yesterday, but we just learned on the previous problem, in order to find the scale factor, all we have to do is just take the scale factor of the area is take the area and multiply it by itself. Or not, oh my gracious, all that made no freaking sense. I just heard it in my own head, and it makes no sense. So let's go back. All right, so how do we find the scale factor of the area? Well, based on the previous problem, basically to find this scale factor right here, all we had to do was take the scale factor of the lengths and square it. So 2 times 2 was 4. So let's see if our theory stands true. Let's find the areas. So the area of the smaller circle, remember, is just pi times r squared, which would be 4 squared times pi, which would be 16 pi. Now, I'm not going to multiply by pi, and I'll show you why. Okay, so 8 units. So this is pi r squared again, or 8 squared times pi. Well, 8 squared is going to be 8 times 8 is going to be 64, so 64 pi. So those are my those are my units. 16 pi, 64 pi. That's my area. So now let's see if we're right. 64 pi divided by 16 pi. Well, pi divided by pi is just going to be 1. So we're looking at 64 divided by 16. Well, let's see. We're saying it's 4, so let's see. 16 times 4. Let's run out here. 16 times 4 is just going to be 2. 6 times 4 is 24. Carry the 2. 4 times 1 is 4. Plus 2 is going to be 6. So 64. So we're right. It's 4. And our percent was 400%. So we had a theory. We tested our theory. Our theory comes out to being true. So does that mean our theory is correct? Well, I'm not 100% convinced. I want to guarantee it. So I'm going to continue on. I'm going to look at the next problem. I want to see whether or not this theory will continue on problem after problem after problem. If I haven't come across a problem that throws me off, then I think I'm pretty darn good. So let's find out. All right, so we got our last one right here. Remember, drawing 1's the original, drawing 2 is the scale. Okay, so the length of each side in drawing 1 is 12 units, so that's 12. And the length of each side in drawing 2 is 6. So we're going to do the same thing again, scale over the original. Okay, so the original drawing 1's scale was, drawing 1's side was 12, and drawing 2 is 6. So drawing 1 is 12, drawing 2 is 6. So the scale factor would be the scale over the original, or 6 over 12, which would be 1/2. Or that would also be known as 50%. Now, if my theory stands true, all I have to do is take 1/2 and multiply it by itself 1/2 to get 1/4. So my combined area of this one here should be a ratio of 25%. That should be my scale factor in percent for the area comparison. So let's find out if I'm right. So to find the area of a square, we just take 12 times 12, which would be 144 units squared. Area, the second one would be 6 times 6, which would be 36 units squared. So the formula would be, the scale factor would be the scale area over the original area, which would be 144. Now here comes the question. We got to determine whether or not 36 times 4 gives me 144. So 36 times 4. 6 times 4 is 24, carry the 2. 4 times 3 is 12. 12 plus 2 is going to be 14, 144. Well, ain't that just interesting? That's 1/4, which matches that, which means that's correct. It's 25%. So 1/4 is the quotient of the areas. The scale factor was 1/2. So my conclusion stands true. My theory is right. In order to determine the quotient of the areas, if I take the scale factor and multiply it by itself, I'll get the quotient of the areas, or the scale factor of the area in its fraction form and its percent form. So my theory holds up. My theory stands true. So I just figured out that there's a shorter way to find the area without having to ever multiply it. I can find that scale factor lickety-split. So let's see if we can apply this information to a couple of problems. So what percent of the area of the large square is the area of the small square? So what percent of the area of the larger square is the area of the smaller square? Okay, so we want to know what percent this square is of this bigger square. Okay, well, we could just do our typical thing. Now, it wants to know, so it's kind of just a simple little problem here. We can do this multiple ways. We can either use our scales or we can actually use some common sense here. Okay, what percent? So what percent? So let's find out what the combined area of the blue square is. So the blue square. And let's put blue. All right, so the blue area is 5 times 5, which would be 25. The white would be 1 times 1, or 1. So now you got yourself two options. You got 25 over 1, or you got 1 over 25. So the question would be, would this be 2,500%, or would we be looking at 4%? So that's your question. Now, I'm going to pose this to you. We're asking what percent of the area of the large square is the area of the small square. Okay, so what percent of the area of the larger square is the area of the small square? So we're asking, what percent does this square take up of this entire bigger square? Okay, does that little square take up 2,500% of the blue square? No, it doesn't. 2,500% would be an enlargement. That's what you would expect out of that little itty bitty teeny tiny blue one. If that little, I'm sorry, not blue, little white one. If that white one decided it wanted to grow up to be that big giant square, it would have to grow up 2,500%. But we're asking what percentage that little white square is. And that little white square is only 4%. So this is your correct answer. It's going to be the 4% one. Not this nasty 2,500% up here. Okay? Now, I would normally go through all these, but I want to see if some of y'all are actually paying attention. I will give you 25 bonus points if you can come up with the correct answer on this one. Just example 2. We're not going to worry about example 3. Just example 2. If you've been paying attention, if you've been watching everything I did, if you've been listening to everything I've said, then finding the percentage of the area of the large disk that lies outside the shaded disk will let you will be able to figure out this answer if you've been paying attention. So bonus points to the students who get that question right. So that means this assignment is worth 125 points if you give me everything done. That's an extra 25 bonus points if you actually do the work. Okay? Let's go on to slide 6. So here's your spring break homework packet. These are lesson 15 problem set, all the questions again. I just want you to do all the questions. It's not even that hard. It's just a few questions. As a matter of fact, somebody decided to leave their lesson packet here, so I've got everything here. So I'm asking you to do, let's see, where's the problem set at? Problem set for lesson 15 has got 5 problems. It's got some multiples in there, but it's not that big of a thing. So just come back with that done and we're done. So that's lesson 15, problem set, all questions, and you're done. That's the end of this lesson. Again, short, simple, sweet, to the point, not even that much to worry about.